So we have x plus 2 over x squared minus 9 is greater than or equal to negative 4/5. So the first thing we're going to do is move the negative 4/5 over to the left so that we have x plus 2 over x squared minus 9 plus 4/5 is greater than or equal to 0. So now, before we go further, we want to combine this all into one big old happy fraction. So right now, we can't add these fractions together unless they have the same denominator. One fraction has x squared minus 9 for its denominator, and the other one has 5 for its denominator. We need to get a common denominator by multiplying this side of the problem by 5 over 5, because 5 divided by 5 equals 1. So we're not changing the value, we're just changing how it looks when we multiply by 1. So it's going to be 5 times that, and 5 times that. You are definitely going to want to multiply that 5 through the numerator, but I wouldn't multiply it through the denominator because leaving the denominator factored will be a really good idea. Okay, in fact, we're going to factor that further into our x minus 3x plus 3. Now for this fraction here, we want the common denominator x squared minus 9, so I'm going to go ahead and multiply the top and the bottom of this fraction by x squared minus 9. So then I'm going to distribute that through the top, but again, just leave it all factored in the bottom. Okay, so the numerator is going to end up with 5 times x, 5x, 5 times 2, so 10, and then 4 times x squared, so 4x squared, and 4 times negative 9, so negative 36. And that's going to be over our new big old common denominator, 5 times x squared minus 9. We're going to write that out as x minus 3, x plus 3. Okay, let's simplify the numerator. So the numerator would be 4x squared plus 5x minus 26 over 5 times x minus 3, x plus 3. Now that we have that whole numerator combined together, it would be good to have that in factored form, because that's going to be easier to help us find our critical values. So let's go ahead and factor the numerator. This is when we factored in a previous problem when we were doing this problem graphically instead of algebraically. And I didn't really go through the factoring process. We can do that if you want and factor by grouping. But if I remember correctly from what we did before, the factors were 4x plus 13, and then x minus 2. And if we FOIL that back out to check it, let's see, we've got 4x times x is 4x squared. 4x times negative 2 is negative 8x. 13 times x is 13x. And 13x plus negative 8x adds up to our 5x in the middle. Okay, the reason we want this whole thing in factored form is it will help us to find those critical values. And the critical values come from the factors of the numerator are the x-intercepts, and the factors of the denominator are the asymptotes or wholes, correct? So our x-intercepts are going to be at negative 13/4, because that comes from setting this first factor equal to 0 and solving for x. And then at 2, so those are our x-intercepts. And then our asymptotes will be at 3 and negative 3. So we have 4 critical values, and we want to put them in order on the number line from smallest to biggest. Don't forget that negative 13/4, I think I found the decimal for that previously, wasn't that negative 3.25 or something like that? So that is our most left point. So we have negative infinity, and then we would have negative 3.25, and then negative 3, and then positive 2, and then positive 3. So let's go back up to this part that I covered up so that it wouldn't be confusing while we were doing the rest of this. So here's our number line, and on our number line we have our x-intercepts at negative 3/4 and positive 2. And then we have our asymptotes at negative 3 and 3, and I've listed all of those critical values from smallest to greatest on our number line. And then above them I've indicated whether it's a 0 or undefined at that point if it's an asymptote. I just kind of wrote in 0 as an asymptote when I did this last year. Okay. And then also on my number line, I chose to give myself a little more help with my grouping brackets. So because this problem is greater than or equal to, that means we care about where it's equal to. So at our x-intercepts, it can be equal to 0. That's fine. We can do inclusive brackets at those locations. But our asymptotes, we can't have that be part of our solution no matter what. So we have to have parentheses at our asymptotes. I don't know if you can see how I've drawn those in on my number line just to help me out. You know, really how you use that number line to visually represent your problem is really up to you. I've shown you many different ways of labeling it, and this is just another idea for how to keep it straight in your head as to what that number line is actually telling us about the solutions. Okay, so from those 4 critical values, then we have 5 intervals. We have an interval from negative infinity to negative 13/4, closed with a bracket because that's a y-intercept, so I mean an x-intercept, so it's okay if it's equal to 0 there. And then we have from negative 13/4 with a bracket to negative 3 with a parenthesis because that's an asymptote, so it can't ever cross the asymptote. Then we have another interval from negative 3 to positive 2, parenthesis around negative 3 where the asymptote is, bracket around positive 2 because it's an x-intercept where it equals 0. And then from positive 2, where it's a 0, an x-intercept, and it can equal 0, to positive 3, where the asymptote is, so parenthesis there, because it can't cross the asymptote. And then our last interval is parenthesis 3, where it can't cross the asymptote, to infinity. So I know these problems get a little confusing when it's an equal to problem because it's a mixture of parentheses and brackets depending on if the point we're looking at is a 0 or an asymptote. It's a really important thing to remember. Okay, so then I went through and chose a test value in each interval. Since negative 3.25 or negative 13/4 equates to negative 3.25, basically that helps me pick my numbers a little easier. So I chose negative 4 in this interval because it's smaller than negative 3.25. And I chose negative 3.1 in this interval because it's smaller than negative 3 but bigger than negative 3.25. And I chose 0 in this interval because 0 is a wonderful number to use wherever it fits, if you can, unless 0 is actually one of your critical values. And then here we've got 2.5 between our 2 and 3. And then just beyond 3, I chose the number 4. So then you take these test values and you plug them back in to your finished equation from earlier. So that would be this one right here, right? So I plugged in a negative 4 into all of my x values, and I got 18/35. So this is something that you can just, plug into a calculator to get that value. The fact that the answer is 18/35 is not as important as the fact that that answer is positive. Quickly, let's go through and see how we can see that that answer is positive. So 4 times negative 4 is negative 16 plus 13. That gives us a negative. Negative 4 minus 2 is going to be negative 6, which is a negative. And then 5 times negative 4 minus 3, so that would be negative 7. And then negative 4 plus 3, so that would be negative 1. So we end up with a negative times a negative in the numerator divided by a negative times a negative in the denominator. So positive divided by positive gives us a positive result. So like I said, the 18 over 35 doesn't even matter. What matters is that the number we get when we plug those in is positive, because that tells us whether it's above or below the x-axis. Okay, so that's what I've gone through and done for each of these intervals. Apparently when I did this last year, I made a mistake because I've gone in and like corrected it, right? So because this number ended up being positive, that interval is greater than 0, so that makes the inequality true. And then when I plugged in negative 3.1 into my problem, I ended up with a negative divided by a positive, which gives me a negative value, or less than 0, which makes that interval false in our inequality, because it has to be greater than, not less than. 0 is easy to plug in, right? And we get a positive value there, so that that value, any of the values between negative 3 and 2 are going to give us a greater than value, which makes our inequality true. And then we plug in our test point 2.5 and we get a negative value, which makes our inequality false because it's less than 0. Then we plug in our test value of 4 and we get a positive value, which puts our answer greater than 0, which is true. So now we look at each of our 5 intervals and which ones are true, and that is what creates our final answer. So without having a graph to show where it's above or below, we are just simply finding those, is it greater than or less than, by the fact if it's positive, it's greater than, if it's negative, it's less than, and which one of those makes our inequality true. Whew. It might be easier to just graph these, huh? But this is just another way of writing these out without having to graph, with kind of a lot of the same steps. We're comparing this to having done it by graphing previously. We get about the same result.